Homework 2, problem 9. Find the force between two parallel wires, each carrying a current I in the same direction. To do this, we first need to find the magnetic field due to one of the wires, and then find the force from that magnetic field on the other wire. To find the magnetic field, we're going to use Ampere's law. To use Ampere's law, we have to draw a Amperian loop. Here, I'm going to make my Amperian loop turn in this direction. Oops, other way. Turn in this direction. Since that's the right-hand rule, and I kind of know beforehand that that's how it's going to be, I draw my Amperian loop as a circle in order to take full advantage of the symmetry of the problem. And Ampere's law states, the integral form of Ampere's law states that the integral over the edge of this closed surface of dl dot the magnetic field, 1 over mu, should be equal to the integral through the surface d2x n hat dot j, which of course is simply the current enclosed. For our problem, we're going to make the statements that dl is in the, it will be dl in the vector component will be phi hat, and we're going to make the argument through symmetry reasons that the magnetic field will depend only on the distance d, and it will be in the phi hat direction. Now, from these equations, we can go ahead and evaluate this. This dl dot b, of course, is just going to give us the dl without the vector times the b phi as a function of d. But now this is independent of phi here, and so we just need the length around the circuit. The length around a circuit is, of course, 2 pi d. And so the left-hand side of Ampere's law is going to give us 2 pi d times 1 over mu naught times b phi, the function of d. And then the right-hand side is simply the current enclosed, which is I. So this is going to give me the magnetic field, the function of d, is mu naught I over 2 pi d, which is, of course, the known result for a wire carrying a constant current. Now, in order to find the magnetic force on the other object, we use the Lorentz force. The Lorentz force, the way I like to use it, is the integral d3x of j cross b. Now j, if you might remember, how do I know this? J can be written as rho v. Remember, we had that as the definition of what the current density was. And so this is essentially d3x times rho is q, so this is still qv cross b. This is just the form that we need. Now, this integral d3x times j can be written as d2x times some length if we think of integrating over a cylinder. d2x times some length, and then the d2x times j is just going to be the current that flows through it, and then it will have the length. So this is going to be I times L, and now we have to worry about the direction of the current. The direction of the current is going to be here in the x hat direction. So the j hat is going to be in the x hat direction. The b is in the phi hat direction. That's actually going to be, oh, x hat, sorry, I hat. Yeah, I hat. I hat. The b is in the phi hat direction, which here is going to be in the positive k hat direction. So cross b sub phi of d times k hat. So I cross k, I hat cross k hat is minus j hat. And so divide both sides by the length. The force per unit length is going to be mu naught I squared over 2 pi d, and it's going to be in the minus j hat direction. It's going to be towards the other the other object. Now it says compare this to our answer from answer 4. And so let's find where we have that one written. And for that one, we find that it's lambda squared over 2 pi epsilon naught d. So we have I squared, lambda squared, that part looks similar. We have 2 pi d, that part looks similar. And then we have a 1 over epsilon naught and a mu naught on top. Very similar, it turns out, because the structure of the Gauss's law, right, always has a 1 over mu naught times b, but always has epsilon naught times e. So that part looks identical as well. And then the only difference says that the force between 2 line charges is repulsive. The force between 2 wires going in the same direction is attractive. So everything looks very similar between those two.